discussion about Optane, or as it used to be known, 3D XPoint. All right, so actually before we go there, here's an interesting tidbit. I was saying in one of my past videos that whenever things get expensive, people like us, the software engineers, will try to find a way to make it cheaper whenever things like try to find a substitute, right? When memory gets more expensive, we try to find disk or SSDs. And whenever memory gets cheap, we'll become more wasteful. And this is a news article that does basically that. Memory has been expensive for 3 years almost, and the result is there used to be a thing called a memcached. It's a very commonly used open source software that is based on memory, and then it's a key value store. You give it a string key, and then you say you can either write or you can read based on the key, and it will give you a value, or you can put in a value. So with memory being expensive, now we're trying to find ways with a flash or 3D XPoint, Optane, that apparently would achieve very similar results, as you can see here. Transactions per second, using this SSD, it is actually better than memcached that's implemented in AWS. Same thing here. Okay, so with that out of the way, so let's talk about Optane. Let's just call it Optane. It's much easier to pronounce than 3D XPoint. So long. Anyway, so when Optane was first released, Intel promised 1,000 times performance. Okay, so you can think about what kind of 1,000 times. Apparently, it says it's 1,000 times faster than NAND. NAND being the SSDs that we usually use, the thing that is usually inside the SSDs. 1,000 times endurance. Endurance is in how many times a piece of a cell can be written to. So for an SSD, a single level cell is about 1,000 times. So if you write it 1,000 times, it goes bust. It basically, there's a physical wear whenever you write to it, and that the physical wear happens because you had to push in electrons, and the movement of electrons itself messes it up. And that says 1,000 times endurance. Okay, so that means it should be able to be written 1,000,000 times, 10 to the 6. And then it says 10 times denser than conventional memory. So this is comparing it against DRAM. It's this conventional memory. Now, funny thing, so that's 2016 and 2015. And by 2018, this is what they claim. Latency is 10x. Endurance is 3x. IOPS is 4x. What happened to my 1000x? What? All right. And then even later, it says 2.8 times. It's not even 3 anymore. So we went more than 300, we lost more than 300 times of what was promised to us. Right? So I think a lot of the hype around Optane was based on the 1,000 times claim. If that was the case, yeah, it will be very promising, but with a 3x, 4x, or even 10x latency improvement, and this QoS is 100 QoS means like at the range of latency of each write is much tighter. So you don't have things that are 3 milliseconds and things are suddenly you have a 3 millisecond and then a bunch of others are 0. Average maybe 0.5, but then you had one write that is a 3 millisecond. So that is bad. So it's saying it's much tighter. Okay, I'm fine. I can see there are certain use cases when you really care about quality of service in the computer science sense. The quality of service is really like a promise you can put on the worst case scenario. Yeah, there's some use cases for that, but like for most of the use cases that I can think of, you don't care. I mean, if you're, because these numbers are below human sensing threshold. You can't tell between a 3 millisecond thing and a 0.3 millisecond thing. You can't tell, right? It's 10 times better, but you can't tell. And the only time you can tell is when you queue them up. If you have 100 of those things going at 3 milliseconds, and then 100 of these things going at 0.3 milliseconds, yeah, you will tell when is 30 milliseconds, which is less than one frame on a game. One is going to be 300 millisecond, and that's human time scale. You can actually tell there's a delay. But the problem is then you're talking about 100 requests, and at 100 requests, statistics comes in. So you still don't care about quality of service. You care about throughput at that point. Right? So you care about the average at 100, not at 1. A lot more than so it's kind of I don't see too much promises here, but anyways, so that was one claim that they made, and then there are other implications, especially around endurance. So if you look at this thing, this is from Micron. You can see that for DRAM, the endurance is 10 to the 15, which means you can never fit. You can almost never break it. Each cell can be written to. I don't even know how to. It's each cell. So 9 is a billion, 12 is a trillion, and 15 is like a quadrillion or whatever. It's some ridiculous number that I can't even imagine. But okay, so a DRAM basically never breaks. A NAND does break, as you can see here. It's saying 10 to the 5 to 10 to the 3, but actually it's lower than that. They use things to hide it. But even if you stick with this is 10,000 times, and this is 3,000 writes. But actually nowadays these DRAMs don't last that long. I don't know when this thing was written. August 10th. Oh, 2010. Yeah, that makes sense. Because back then the DRAMs, sorry, the NANDs were made with much bigger or older technology, which means their features are much bigger. And if you're bigger, you're more resistant to wear. And back then, everything was single level cells. So you only keep either a 0 or a 1 in a cell. Nowadays, you have these triple level cells or something, and even the quad level cells are there. So which means you keep 9 different levels of voltage inside each cell, and you have to differentiate all 9 of them. And then the other thing is you can never rewrite that single cell anymore. You have to rewrite the entire cell that keeps, in this case, 4 bits. So every time you write, you have to change 4 bits. You can never change 1 bit. But you could never change 1 bit anyways with Flash, with NAND, because there's other issues. You can only rewrite blocks. or pages or whatever. It's not. I forgot the terminology, but regardless of that, you can see you cannot put this NAND stuff, even if it's fast enough, you cannot put it in the DIMM slots to be used as system memory because it will literally wear down and die. Right. So if you think about the way CPU accesses memory, right, even if you look at this there's a couple of things that's needed. First, these memories shouldn't be shifting around because every time you shift around, you have to change mapping in your page table. That's expensive. And then the other thing is, what about your page table? If you keep changing your page table, now your page table gets worn down, right? So your page table is fixed usually, in at least for the kernel mapping is fixed. Now, sorry, the page table is just a translation from virtual address to physical address. And each program actually has its own virtual space, so they can't mess each other up. For example, if I'm Word, I cannot write in Excel's memory space. So that is the way we kind of separate these processes, these programs. So you can see a lot of these things are actually fixed in memory. So, and then they get changed a lot. And when I say change a lot, if you just scroll this page, right? Every time you scroll, a bunch of cells, a bunch of writes happen. Like every time anything changes in your screen, just anything changes in your screen, your memory is changing. Something is writing to your memory. So you can imagine there's a lot of writes happening to memory, but you don't care because it has almost infinite, or for all practical purposes, infinite amount of writes. By the time the thing dies, probably you don't want to be using it anymore because maybe you have like a, back then they had 2 megabytes memory, right? Now we have 32 gigabytes memory if you're rich enough. So you don't care. But if you put a NAND there, yeah, you get 10,000 writes. Even back then, nowadays, you get 1,000 writes if you're using single level cells. And your computer will break. It would give you blue screen of death or whatever other things you get. So the claim initially for Optane is that it's like NAND in the sense that it keeps the data. It's non-volatile, so it keeps the data when power is off. And it has 1,000 times the endurance. So basically becomes 10 to the either, sorry, 10 to the 5, that's 100K. I'm going crazy. Yes, that's 100K. But we don't have that now. I can tell you we don't have that now. But this thing, let's say with 10 to the 4, right, something like that. Let's say 10 to the 4, 10,000 times. You give it another 30, now you're at 1 million times. Now you can write the same cell 1 million times. And then Optane is good in the sense that it can change individual bits instead of entire blocks. So that keeps the wear amplification down. So instead of writing 1 bit in NAND is writing a 4K block. So I think it's a 4K block. I might be wrong. Don't quote me on it. But it's much bigger. It's much bigger than bits. It's kilobytes, right? So 3D XPoint doesn't have that Optane doesn't have that problem. So maybe you can get away with using it for, maybe you have some special protocol with CPU so that it doesn't put the things that it knows that's frequently changing on you. For example, the page table, or things that have to be kept on getting written to. Let's say the stack of your program, which is getting changed all the time. Every time there's any function call, any change usually happens on the stack of your program. So don't put it there, and then you put the other stuff in there. Maybe it works. you can even use it as some really low latency, almost like disk, and if you had the thing that's promised. If you look, this is important too. So the thing that was promised, which was 1,000 times faster than NAND, right? And if that applies to latency, NAND latency is about 1 millisecond or less, 0.5, 0.3, something like that. Divide by 1,000, you're looking at 300, minimum 300 nanoseconds, which is on par with DRAM. DRAM goes about 100 millisecond. Nanoseconds. Typically, I think the latency is like from 80 to 150, around that level. So you're at 2x, so you're 2x slower in terms of latency, and in terms of bandwidth, it might be very fast too. I don't know. Nothing tells me that there's a particular thing that limits the bandwidth of Optane. So yeah, you may be able to substitute that, and that's indeed what Intel promised. Intel had this thing called, what the hell is it? This. They said, okay, we're gonna have, you can see it looks like a memory stick for the people that have seen a memory stick. You're saying, oh, you can have a higher density, cheaper, and faster DRAM that's also non-volatile, that's persistent. Sounds great to me. Says it's gonna come out second half of 2018. This is now 2019. Nothing. Why? Because endurance is not there. You cannot have a thing that wears down in, nowadays maybe 30,000 times or something. There was a guy that made so this memory guy, if you guys want, you should read his stuff. Is very knowledgeable on a lot of things. I actually wrote him an email, and I asked him what he thought about my theory of trying to look at the capex cycle to predict capacity in 2 years, and he agreed with me, and he's been writing this for like 30 years. This guy's like a super old guy. Anyways, cells write for erase per lifetime. Optane 33,000 times. I mean, this one is a SSD. It's also 31,000 times, but this is actually this is misleading. They're using some error correction stuff here, and that error correction thing is I think it's like low. I forgot. It's a parity-based error correction thing that spans multiple cells. So whenever an error is detected, it could be very costly to figure out what it actually is. So when a cell breaks, which is a probabilistic event, as the probability goes up as you keep writing to it, your read performance will suffer a lot as well. Not just write, your read performance will suffer and becomes very unpredictable how long it takes to read. So you get spikes in latency. So yeah, so that is not really representative, and the things that are more representative are like these numbers. Consumer grade, they don't over provision as much. They use multi-level cells and 3-level cells and even quad-level cells. So these are the more realistic numbers, like 500, 100. So we're working with hundreds. So yeah, I mean, 30,000 is okay for a disk. It's fine. Like, how often do you rewrite a disk 30,000 times? Probably not. Most of the time you just read. But for memory, this doesn't cut it. This has to be at least 100 times better, at least, if not more. Right, so this is not coming until Intel fixes the endurance issue. But who knows? They haven't promised anything. The only thing we've seen is they kept on saying things are worse and worse. Now ultra endurance is only 2 times 8. So from 1000. Good luck. Yeah, and in terms of pricing, I mean, you can get a 375 gig Optane with PCIe connection, or you can get a 2 terabyte SSD for with a PCIe. Same price, except 6 times storage. I mean, you be the judge. Yeah, this thing gets lower latency at low queue depth. So if you write one thing at a time, this thing is super fast at 16 queue depth. So if you have 16 things that's queued up that needs to be executed, this thing like saturates its performance, the bus, so it's completely saturated. For SSD, this thing needs like 200 queue depth. You need 200 things in your queue to saturate the bus, at which point it becomes very hard to differentiate against this thing. But you're talking about really like 20 microseconds versus something like 500 microseconds or 0.5 milliseconds. As a human, you really can't tell. And whenever you have many of these things happening at the same time, well, latency is no longer the concern here. Throughput becomes the concern. IOPS becomes the concern. And in terms of IOPS, this stuff, I can tell you, this stuff does something like 500,000 per second. But a decent SSD can do 360,000 per second. These are all mind-blowing numbers, right? So, and this thing is per gigabyte 1/6 the price, or 1/5 the price, however you want to look at it. So the revolution isn't coming. Oh, and the other thing that I don't know is I still don't know what the hell is Optane. I know they drew these pictures, but what is it? Is it phase changing? Is it based on same quantum effect that Flash uses? Don't know. I haven't seen anything. If anyone has seen anything like a document that can teach me what it actually is, it would be great to know. I mean, but I'm guessing it's some kind of phase changing thing instead of like a quantum tunneling based thing. But I'm guessing. I haven't found anywhere how, like, what the underlying like physics is for Optane to work. I mean, obviously it works. So it's not vaporware, and obviously it's not NAND, because a lot of the numbers don't lie. They're better. They're clearly better, but also a lot more expensive and not nearly as good as they promised it. So yeah. People that are super long Optane or 3D XPoint, they look at these numbers, and then you have to rethink whether that promised land is near. Anyways, see you next time.